All right, so earlier this course, we were introduced to the opportunity cost study, which found that students became thriftier when they were reminded that not spending money now means that money can be spent on other things in the future. So let's reanalyze this data in the context of a normal distribution and compare the results to the simulation tests we did before. So we originally looked at the study as a one-sided test, but since we're going to do everything else this quarter with two-sided, let's do it with a two-tailed test instead. So the null hypothesis is that reminding students that they can save money for later purchases will not have any impact on the student's spending decision. That is, the difference in the proportions between the two groups is equal to 0. The alternative is that reminding students that they can save money for later purchases affected whether or not they continue with a purchase. That is, the difference in proportions is not equal to 0. Based on the sample we had earlier, the null value, the proportion of success that not buying the DVD from the treatment group is 34 out of 75, and the control group is 19 out of 75. So if you subtract the two, you end up with a 20% difference between the two groups. This will be our point estimate. Let's imagine I ran 100,000 simulations on this, and I found with a p-value, a two-tailed p-value of about 1.6%. Because this is a lot less than 5%, we would reject the null hypothesis. There is sufficient evidence to suggest that the reminder had an effect on whether or not the student continued with the purchase. Now, because the point estimate was positive, we have evidence that the reminder caused students to be thriftier. But what if we used the normal distribution instead? Well, this figure here summarizes the null distribution as determined by the randomization method. And behind it, you see a normal curve. And that normal curve fits pretty well. The standard error of that normal curve is 0.078. And if you recall, the point estimate is 0.2. It is helpful to draw and shade a picture of the normal distribution so we know precisely what we want to calculate. Here, we want to find the area of the two tails represented by the p-value. For that, we need what's called the test statistic. And essentially, a test statistic is a measure of the distance between the null value and the point estimate. It is a z-score, and it's given by the formula of point estimate minus null value over standard error. In this case, the opportunity cost study, we found the point estimate to be 0.2, the null value was 0, and I'm going to just go ahead and give you the standard error is 0.078. So the test statistic in this case is 0.2 minus 0 over 0.078. That comes out to be 2.56. Now, z-scores in general always have a mean of 0 and always have a standard deviation of 1. So if I want to find the area underneath the curve and beyond 2.56, well, I would use a normal distribution. So calculator goes second, vars. I'll choose the normal CDF. And then I would enter 2.56 to 999, the mean of 0, standard deviation of 1. And then paste it. Whoops. And I get 0.005. However, this is a two-tailed test, so I would want to look at the left tail and the right tail. So I'd also want to multiply that answer by 2. So 0.0105. So for a two-tailed test, we multiply by 2 to get normal CDF 2.56, 99901 times 2, 0.0105. So in general, the p-value is found using normal CDF. Just whatever the test statistic is, take the absolute value, so chop off any negative sign. Just use the positive version of the test statistic. To some large number, 999 is always going to be more than sufficient for this. Then 0.1. So use the absolute value of the z-score, that is, make sure that you're using a positive value. So just remove any negative sign if you happen to have a negative test statistic. Go to something arbitrarily big. 999 will be more than sufficient for this test. Z-scores always have a mean of 0 and always have a standard deviation of 1. And then we multiply the results by 2 to account for the other tail. Again, so just to summarize, for the opportunity cost study, the point estimate was 0.2, mean of 0, standard error 0.078. The z-score, the test statistic, is point estimate minus no mean over the standard error, which is 0.2 minus 0. And then that divided by 0.078, you get about 2.56. And then the p-values found by doing the normal CDF, starting with that test statistic 2.56 to 999, 0.1 times 2. So 0.0105. If you notice this p-value, 0.0105, or about 1.1%, is similar to the two-tail test two-tail p-value we got from the randomization approach, which is about 1.6%. And this is because the study had random assignment, and was large enough for the conditions of the central limit theorem to use. The null distribution can be reasonably approximated by the normal distribution.